Okay, hi guys. So we'll be continuing more on the effect of catalyst into the reaction coordinate. So suppose for an example we have this reaction in which the reactant is converting into products. So let's suppose the forward reaction is fast and the backward reaction is also fast. So we would have graph something like this, wherein potential energy with reaction coordinate would be something like very fast happening like this. And second, if we have reactants which is converting into products at a slow rate and product also converting into reactant at another slow pace, then we would have graph something like between potential energy and reaction coordinate as something like this. Okay, and on the third case, if we have R and P where the reaction to product formation is fast but product to reactant formation is slow, then we would have the graph something like again of potential energy and reaction coordinate as something like this. Okay, now let's draw another elaborate graph where C is termed as catalyst and I is the intermediate product. So suppose we have this reaction graph. On the y-axis we have potential energy and on the x-axis we have reaction coordinate. Suppose we have graph like this. Okay, so this is initially the reactant, or we can say this is reactant is present along with catalyst. Okay, so this is the activation energy which is required here, and here R1 and catalyst would be present. So this is the activation energy or EA1 which is required. Then after this intermediate product is formed, then other the activation complex is formed, this intermediate product is formed. Okay, and the formation of this product happens at this energy level, so this is nothing but delta H1 or delta E1. So this is nothing but product P or intermediate, or which is R2 or the reactant for the second reaction. So for a second reaction, EA2 as the activation energy would be required, and here R2 plus C or rather R2 plus I would be here. Okay, and finally, so this is in this activation complex R1 and C were formed or were clubbed together to form the intermediate or other activation complex, and this C was consumed in the formation of this product and also in the activation complex. Okay, and finally some product was formed here which would be acting as a reactant for the further reaction, and in this activation complex the intermediate gets attached with I2 to form gets attached with R2 to form some intermediate complex 2 here, and then finally we would have formation of P2 along with catalyst. So catalyst is regenerated in the process, and this would be delta E2. Okay, so the overall energy delta A2 or delta H2, whatever you can write. So for the consistency sake I am writing delta H2. So the overall delta H can be written as, this is the overall delta H, which is delta H overall, okay, which is the energy difference of the product with the reactant, okay. So in here we have a product P1 formed along with the intermediate which is formed at this position or at this reaction coordinate, and we are also introducing some R2 here. So R2 and I will again react with each other to form the activation complex 2 here, and from the activation complex 2 here we get formation of P2 along with the catalyst which is regenerated in the reaction, okay. So let's now see another example where we have R1 plus R2 in presence of a catalyst C forms P1 plus P2. So let's look at the elementary step 1. So at elementary step 1 we can say that R1 plus C reacts to form P1 plus I. This is an endothermic process. So for an example, let's associate this example with the previous graph, which is an example of an exothermic graph. So we can say that the elementary step 1, which is the reaction of R1 plus C with rather R1 plus C to form P1 plus I. So this is P1 plus I formed here. So this from R1 to P1, it would be an endothermic process. As we can see, delta H is required, or delta H is the overall energy is positive in this case. So this is an endothermic step, and elementary step 2 would be there is another R2 introduced into the mixture or into the reaction, which reacts with I to form P2 plus I, P2 plus C rather, P2 plus C, which is a exothermic process. As you can see here that for this graph, this was the reactant and this is the product. So this is clearly exothermic process because delta H2 would be negative in this case, as the energy of a product is lesser than the energy of a reactant. And if we see the overall reaction, then overall reaction is also delta H is negative because the energy level of reactant is greater than the energy level of the formed products, okay. And overall complex reaction would be R1 plus R2 gives P1 plus P2, okay. So with this we come to the end of this lecture. In the next lecture we'll be seeing types of catalysis process. Till then, good luck and goodbye.